In 2010, the United States Navy fired a projectile at Mach 7 from a gun with no gunpowder, no explosive warhead, and a range of 100 nautical miles. The test footage went viral. Defense publications declared it a revolution in naval warfare. Pentagon officials called it the most significant advancement in naval gunnery in a century. Admirals spoke of a future where American warships could hit targets anywhere within a 100-mile radius with a projectile the size of a football, traveling faster than a rifle bullet, guided to within meters of its target, and costing less than $10,000 per shot. 11 years later, the Navy quietly canceled the entire program. $500 million spent, 15 years of research and development, hundreds of test firings at the Naval Surface Warfare Center in Dahlgren, Virginia, contracts with BAE Systems and General Atomics, congressional hearings, public demonstrations, and in the end, a weapon that never left the test range, never sailed on a warship in operational service, never fired a single shot in anger. The electromagnetic railgun, the weapon that was going to change everything, is dead. Officially paused in the language of the Navy's statement. Realistically, canceled. The technology that looked like science fiction made real in 2010 turned out to have fundamental engineering problems that 15 years and $500 million could not solve. And here is where the story gets genuinely interesting. Because while the United States was spending that $500 million and ultimately walking away, Japan's defense ministry was watching, studying, and doing things differently. In September 2025, the Japan Maritime Self-Defense Force conducted the world's first successful at-sea test of a ship-mounted railgun aboard the JS Asuka. A real ship, real ocean conditions, real firing. Hypersonic projectiles launched from a naval vessel at sea for the first time in history. The country that invented the weapon's modern concept. The country that built the two most advanced railgun prototypes ever constructed. The country that spent more money on this technology than any other nation on Earth. That country is watching Japan fire railguns from ships while its own program sits in a warehouse in Virginia. How did this happen? And what does the story of the American electromagnetic railgun tell us about the gap between military technology ambition and military technology reality? To understand why the railgun failed, you have to understand what it was supposed to do and why those goals were compelling enough to justify 15 years of investment. The concept is physically elegant. A conventional naval gun uses a chemical propellant, gunpowder, or a similar explosive charge to generate the pressure that accelerates a shell down the barrel and toward the target. The velocity and range you can achieve are constrained by the physics of chemical propellants. You cannot push a projectile faster than the expanding gases behind it will allow, and there are practical limits to how much propellant you can pack into a shell casing and still have the gun survive the firing event. The largest naval guns in history, the 18-inch guns of the Japanese battleship Yamato, could fire a shell weighing over a ton to a range of about 26 miles. That was the upper boundary of what chemistry could achieve. An electromagnetic railgun throws away the chemistry entirely. Two parallel conducting rails connected to an enormous electrical power source generate a magnetic field when current flows through them. A conductive armature, bridging the gap between the rails, experiences a force in that magnetic field, the Lorentz force, that accelerates it down the track. If you put a projectile in front of that armature, the projectile goes along for the ride. The faster you want to go, the more current you push through the rails. The limiting factor is not chemistry, but physics. And the physics, at least on paper, allowed for velocities and ranges that no chemical propellant could match. The Navy's program aimed for a projectile velocity of Mach 7, roughly 5,400 miles per hour, and a range between 50 and 100 nautical miles. At those velocities, the kinetic energy of the projectile alone, without any explosive warhead at all, is sufficient to destroy most targets. A chunk of dense metal traveling at Mach 7 does not need an explosive to be lethal. The physics of kinetic energy at those velocities produces an impact effect equivalent to a vehicle traveling at highway speed running into a wall. Multiply that by the mass of a railgun projectile, and the destructive potential is obvious. The cost argument was equally compelling. Conventional naval missiles, the Tomahawk, the SM-6, the LRASM, cost between $1 and $2 million per shot. A railgun projectile, essentially a shaped block of dense metal with some guidance electronics, was projected to cost between $1,000 and $10,000 each. In a sustained conflict where a warship might need to fire hundreds of weapons against a swarm of incoming threats or a large number of dispersed ground targets, the cost difference between missiles at $1 million each and railgun rounds at $10,000 each is potentially decisive. The Navy envisioned a future where a destroyer could carry thousands of railgun rounds and conduct sustained fire missions that would be financially impossible with conventional missile arsenals. The safety argument completed the case. Every explosive warhead stored on a warship is a potential catastrophe if the ship takes damage. The fires that have resulted from weapons storage impacts on naval vessels throughout history, from Pearl Harbor to the Forrestal Fire in 1967 that killed 134 sailors, are testament to the danger of storing large quantities of explosive ordnance in a confined metal hull. Railgun projectiles are inert metal. They contain no explosive material. A hit on a ship's railgun ammunition storage is not going to trigger a catastrophic secondary explosion the way a hit on a missile magazine might. The safety case alone was worth serious investment. So the concept was compelling. The physics were real. The test results in 2010 were genuine. A 33 megajoule shot at the Dahlgren facility, a world record at the time, demonstrated that the fundamental electromagnetic acceleration principle worked at the velocities and energies the program was targeting. The Navy had real engineers, real contractors, real laboratory results, and a real theoretical framework for a weapon that could change naval warfare. The problems emerged when theory met the engineering reality of building a system that could work repeatedly, reliably, in the corrosive and vibration-heavy environment of a warship at sea. The first problem was the rails themselves. When enormous electrical current flows through the conducting rails and the armature bridges the gap, the rails do not merely experience electrical stress. They experience mechanical stress, thermal stress, and electromagnetic stress simultaneously at levels that no material available to the program could withstand indefinitely. Every firing eroded the rail surface. The contact point between the armature and the rail, moving at hypersonic speed, generated temperatures that exceeded the melting point of copper. The rails were literally consuming themselves with each shot. Early in the program, the rails needed replacement after just a handful of shots. By 2014, Chief of Naval Research Admiral Matthew Clunder claimed the weapon's durability had improved to over 400 shots. But the Office of Naval Research refused to confirm whether those 400 shots were at full power. The question of how long the rails would last at full combat-level energy levels was never satisfactorily answered. For a conventional naval gun, barrel replacement is a known and manageable maintenance event. Barrels of standard naval guns last for hundreds to over 1,000 rounds before requiring replacement, and replacement is a routine shipboard or depot maintenance procedure. A railgun that needed its conducting rails replaced after a few dozen full-power shots would create a maintenance burden that was operationally unacceptable. A warship cannot pause combat operations while the crew replaces the conducting elements of its primary weapon system. The logistics of carrying replacement rails, the time required for the replacement procedure, and the vulnerability of the weapon during that downtime were problems that the material science available to the program could not solve. The second problem was power. Generating the electromagnetic field required to launch a projectile at Mach 7 requires an enormous pulse of electrical energy, on the order of 25 megawatts delivered in a fraction of a second. To put that in context, 25 megawatts is enough electricity to power approximately 19,000 average American homes simultaneously. Delivering that kind of power in a rapid pulse requires a massive energy storage and conditioning system, and then doing it repeatedly at a tactically useful firing rate requires a power generation capacity that was beyond what most naval vessels could provide. The Zumwalt-class destroyer, with its integrated power system generating 78 megawatts through its marine gas turbines, was the only class in the Navy's surface force that could potentially provide the power a railgun needed. The original plan was to deploy the railgun on the Zumwalt class, but the Zumwalt class itself became a program in crisis. Originally planned for 32 ships, the class was reduced to just 3 hulls as costs spiraled. 3 ships was not a viable operational platform for deploying a new weapon system that required an entirely unique power infrastructure to operate. You cannot build a tactical doctrine around a weapon that can only exist on 3 ships. The third problem was range and relevance. The railgun's 100 nautical mile range had seemed impressive in 2005 when the program began. But the threat environment was changing faster than the railgun program was progressing. By the time the program reached its peak investment in the mid-2000s, China had deployed land-based anti-ship missiles with ranges of 200, 400, and eventually over 1,000 nautical miles. A warship would have to sail into a dense threat envelope to get close enough to use a railgun. Hudson Institute analyst Brian Clark put it directly. A Navy vessel could not employ the gun without putting itself within range of a barrage of enemy missiles. The railgun's range, impressive by the standards of naval guns, was inadequate by the standards of the threat environment it was supposed to operate in. Simultaneously, the alternatives were getting better. Hypersonic missiles, long-range precision strike weapons, and directed energy systems were all advancing. The conventional prompt strike program, designed to give Navy surface ships a hypersonic strike capability with ranges of over 1,000 nautical miles, offered a qualitatively different solution to the same problem the railgun was supposed to solve, with far greater range and without the power and rail degradation problems. When the Navy had to make a budget decision in 2021, the choice between continued railgun investment and accelerating hypersonic missile development was not a difficult one. The official statement from the Navy was characteristically bureaucratic in its language. Given fiscal constraints, combat system integration challenges, and the prospective technology maturation of other weapon concepts, the Navy decided to pause research and development of the electromagnetic railgun at the end of 2021. Every phrase in that statement is doing work. Fiscal constraints, combat system integration challenges, prospective technology maturation of other weapon concepts. Translated, we ran out of money. We could not make it work on a ship, and something better is coming. Admiral John Richardson, who served as Chief of Naval Operations, was more candid in a 2019 interview at the Atlantic Council before the program was officially canceled. He described the railgun as the case study that would say, this is how innovation maybe should not happen. Coming from the Navy's top uniformed officer, that is a remarkably direct admission that the program had gone wrong in ways that went beyond technical problems. The innovation process itself had failed. The valley of death that technology development programs sometimes fall into, where promising research cannot make the transition to fielded capability, had claimed the railgun despite enormous investment. What makes the American railgun story particularly pointed is what happened in Japan while the United States was spending 15 years and $500 million failing to field the technology. Japan's railgun program began in 2016, 11 years after the American program. It was developed by the Acquisition, Technology, and Logistics Agency under the Japan Ministry of Defense, with a focus on naval applications and specifically on the need to counter hypersonic missile threats from China, Russia, and North Korea. Japan's approach was methodical, focused on specific performance targets, and built around solving the power and rail degradation problems as engineering challenges with defined solutions rather than aspirational goals. In October 2023, Japan announced that it had conducted the world's first shipboard firing test of a railgun aboard a test vessel operating with the Japan Maritime Self-Defense Force. And in September 2025, Japan went further, conducting at-sea tests aboard the JS Asuka with what defense analysts described as genuine sustained fire capability, launching projectiles at Mach 7 with 20 megajoules of energy. Japan signed railgun technology cooperation agreements with France and Germany in May 2024, creating a trilateral research partnership that is now the most advanced operational railgun development program in the world. The country that invented the modern electromagnetic railgun concept, that built the largest and most powerful test prototypes, that spent more money on the technology than any other nation, has no operational railgun. Japan, starting 11 years later, with a fraction of the budget, has fired one from a ship at sea. The comparison is uncomfortable for American defense acquisition in ways that extend beyond the railgun program specifically. It raises questions about why a program can spend 15 years and $500 million on a weapon and end up with nothing operational, while an allied nation with a smaller defense budget and a later start achieves at-sea testing in less than a decade. Part of the answer is focus. Japan's program was oriented from the beginning on solving specific engineering problems, particularly the rail degradation and power conditioning challenges, with defined performance targets. The American program was oriented around a more ambitious set of capabilities and suffered from the characteristic American defense acquisition tendency to add requirements and extend timelines rather than accepting a less capable but achievable design. Part of the answer is also the valley of death problem in American defense acquisition more broadly. Programs that show promise in research and development frequently cannot survive the transition to procurement because the funding model for that transition requires a different budget process, a different set of advocates, and a different level of institutional commitment than keeping a research program alive. The railgun had plenty of advocates in the research phase. It did not have a viable path to procurement that the budget process could sustain. The hypervelocity projectile, the guided ammunition developed for the railgun that can also be fired from conventional naval guns at lower velocities, is the one piece of the railgun program that survived cancellation. The HVP can be fired from the Navy's standard 5-inch guns at roughly Mach 3, achieving twice the range of conventional rounds with guided accuracy. It is not a railgun, it does not achieve Mach 7, but it does extend the capability of existing naval guns with guided precision at a cost far below conventional missiles. The HVP is the practical residue of 15 years of railgun research, a useful but modest consolation for the investment that was made. The directed energy systems that partly replaced railgun investment are showing genuine promise. High-energy lasers, tested aboard Navy ships over the past several years, offer a cost-per-shot measure of essentially the cost of electricity and can engage small drones, cruise missiles, and fast attack boats at ranges and with an effectiveness that is genuinely useful. The solid-state laser technology maturation program and the high-energy laser with integrated optical dazzler and surveillance system have both demonstrated real capability in at-sea testing. They are not Mach 7 hypervelocity weapons, but they solve different problems, and they solve those problems with a reliability that the railgun never achieved. The conventional prompt strike hypersonic missile program, which will replace the advanced gun system turrets on the Zumwalt-class destroyers, gives those ships a 1,000-plus nautical mile strike capability that the railgun's 100 nautical mile range could never have matched in the evolved threat environment. The trade-off is cost per shot. A hypersonic missile is expensive. A railgun round was projected to be cheap. In a sustained conflict requiring thousands of shots, the cost difference matters enormously. But a weapon that costs $1,000 per round and cannot survive repeated firing is not actually cheaper than a weapon that costs $1 million and reliably hits its target. The lesson of the electromagnetic railgun is not that the technology is impossible. Japan's September 2025 at sea test demonstrates that it is not impossible. The lesson is about what happens when a program tries to be revolutionary rather than evolutionary, when it sets performance targets that exceed what available materials science and engineering can reliably support, and when the acquisition system cannot sustain the transition from promising research to fielded capability. The railgun's failure is a program management and acquisition failure as much as it is a technology failure. The Navy's future surface force will likely not include a railgun in the near term. The Zumwalt class, the only platform that could have powered one, is being converted to carry hypersonic missiles. The destroyer and frigate classes that make up the bulk of the surface force use the same power systems they always have and have no near-term path to the 25-megawatt pulse power generation the railgun required. If the railgun technology matures, if Japan's success drives American renewed interest, if the rail degradation problem is solved through advanced materials, and if a surface combatant platform is designed with the power generation capacity the system needs, the electromagnetic railgun might yet appear on an American warship. But that future is measured in decades, not years. $500 million, 15 years. The world's fastest projectile, fired in a laboratory, photographed and celebrated, and then quietly put in storage while Japan sailed into the Pacific and fired one from a ship. That is the story of the weapon that was going to change everything. If you want to understand where the U.S. Navy's weapons development is actually heading, how directed energy and hypersonic systems are replacing the railgun's unfulfilled promise, and what the competition with China over advanced naval weapons means for the future surface fleet, subscribe to Navy Power Decoded. Every week, we go deeper than the headlines and look at the technology and the decisions that actually shape American sea power. The railgun is dead, but the competition to field the next generation of naval weapons is very much alive.